In this video, I'm going to show you how to use Duhamel integration to obtain the response to a half sine wave impulsive load using my CAS calculator. So the first thing I do is I clear all the single character variables with this command. And I'm gonna have to also clear 4 variables that are more than 1 characters. First of all, P naught, the amplitude of the force, tau, my integration variable during Duhamel integration, omega 0, which is the natural frequency of the structure, and T1 being the duration of this impulse. So I'm going to delete all 4 variables here. And according to my Duhamel integration formula here, I can obtain the response, but I'm going to do it in 2 shots. First, I will obtain the response in region 1, where the load is being applied, and then I'll also have to seek the response outside of that region. I call that region 2. So first, let me get my deflection for region 1. I'll call it D1, and its colon equal to, first of all, some constant 1 over. This, by the way, is an undamped structure assumed, so it's just m times omega 0. And then I have the definite integration going from 0 to t, and of course it's understood that this t remains within region 1. And I forgot to define the p, so let me put it back here. The force p is going to be some p naught times a sine function of this quotient being the argument. And namely, it is pi times tau, my integration variable, tau, over t1. So if you think about this function, when tau is exactly t1, is the first time that it picks up pi, okay, in the sine function, so it becomes 0. So that is the correct description for it. So once I've defined p, I can put it inside my Duhamel integration, and it's also multiplied to my omega naught times, okay, it's getting crowded here. Let me put it on the computer view. So omega 0 times t minus tau is what we have from the Duhamel integration chapter. That's the time elapsed since the impulse at tau was applied. And of course, that's over t tau. Right, so that is my response for region 1. Let's also get it for region 2. So I just copy the above and change D1 to D2. And the only difference is the upper integration limit, because I'm no longer looking at some t inside of this region, but I'm looking at some t outside, in which case I just need to integrate from 0 to t1 and finish, because afterwards there's nothing more in p to integrate. It's p being 0. So that is my response for region 2. All right. And you notice that the function involves, or the output involves omega naught and m and t1 and so on. We're going to simplify that a bit, but first, let's define something that we can use for both regions. So let's define that as a function of t, and it's colon equal to, first of all, if you have a negative time, then of course there is no response, because there is no vibration. Give me 0. Otherwise, I'm going to check when t is before t1, then give me d1, some function of t. Otherwise, it must be outside of t1 or beyond t1, then give me the second response. So that's done. It's a function of t. Now let's think about this. First of all, I would like to rescale length units by doing this. Okay, let me define something called R1, which is equal to D1 divided by the static deflection P0 over K. So we are in a sense just rescaling length units. Now this is a bit messy. I would like to use two dimensionless parameters, namely alpha and beta. Alpha is a rescaled time unit. So let's look at its definition. It's just time over T1. So how many units of T1 has elapsed in terms of time? That's kind of my natural measure of time. And also, although there is no real sine wave going up and down, let's also define some omega being 2 pi over 2T1. Okay, that's as if that sine wave actually could repeat itself. Then 2T1 would be its period. And therefore, let's also define some beta that looks like a frequency ratio, although there's no really not much oscillation going on in that driving force. So it is defined just as omega over omega naught. So if you look at the definition of omega, then it's a pi over T1 over omega naught. That's my beta. So it's a dimensionless quantity. Okay. So I'm going to make use of these to define some substitution rules, which will hopefully make my Km, omega naught, and so on all go away, including T1. And what remains will be just my alpha and beta. Okay. Alpha being the natural measure of time and beta being the so-called frequency ratio. So let me define some substitution rules. Let me just call that subs. It's just several statements telling me what to change into what. So first of all, we know that Km and omega naught are related. So K is namely M times omega naught squared, right? Because omega naught is square root K over M. And another thing, omega naught, according to here, you can rewrite it as a pi over beta T1. Okay, so I'm going to make that substitution in the next line to come. But first, let me define the substitution rule. It is going to be pi over T1 times beta, which I'll just write as B. It's a clean variable. And, okay, if you want to find that, you can also press the book key. End word is here. And every T1 that I'm going to see, I will replace it with this thing, because alpha is T over T1. So T1 is T over alpha, which I just call it A. So let's see what happens when I make all these substitutions into my R sub 1. Okay, so let me just redefine it as itself, but with all those rules being applied, substitution rules. It becomes a very simple expression involving just alpha and beta. All right, so by the same token, I can define my R sub 2, which is the response out there in region 2. So it will be the second Duhamel integration that I did, but this time let me make the substitution here. So you see the result is also quite simple. Now let me go ahead and plot these things. Okay, I would like to plot this so-called response ratio. So let me define it as R plot. It will be some function of x, because that's convenient to plot. So x plays the role of A, okay, the natural time unit. So if time is negative, then I don't need any plot. Otherwise, I'm going to check if time is, the natural time is less than 1, that means time is less than T1. Okay, so if x is smaller than 1, then give me R1 with A becoming x, the plotting variable. Okay. Otherwise, give me, because I must be outside of a T1, okay, or beyond T1, so give me the second response function. Of course, with A rewritten as X. Okay, so there's a function of X that you can plot. So let's now go to insert a page. If you're in the computer view, you can click this button and right click here and insert a page and select graphs. And let me just put our plot here and see what happens. Nothing really gets plotted because I have a symbolic B there, meaning beta, that's not specified, so nothing can be plotted. It doesn't know what to do. So you can also press this button, action, and insert a slider here. So my slider will be on B, and the value means the first time it appears. Okay, perhaps let's make it 1/4 or 0.25. And we can enter it like that. The minimum, let's go to say 0.1 or 0.01. Maximum, okay, let's go to maybe 5. Okay, maybe in steps of 0.01. Okay, so let me now zoom in a bit. So you see we can make beta go to different values and the graph will change. Let's see, settings. I would like to have it not minimized. So let's try some different beta values. For example, in here, I have 1/4, which is close to this. You can also use this button to change. So here's beta equals 1/4. And we can, of course, measure the maximum by coming to tools, analyze graph and maximum. Let me just get the overall maximum by giving it a wide range of upper and lower bound. So that is my maximum response ratio being 1.27, and it occurs at a time value of 0.4. That means less than T1. All right, let's see what happens when beta value, or the so-called frequency ratio, increases. So we can press this button to make it increase. Perhaps let it go to 1/3. Okay, something like this. We see the maximum response is approximately 1.5. And still, the time that happens is before the load disappears, right? Because this means T is less than T1. This variable here on the horizontal axis is the ratio of time to T1. But let's keep on going. Let beta go to perhaps 1/2. Okay, still we have the maximum happening somewhere before time hits T1 or alpha hits 1. Okay, let's zoom out a bit. Here, zoom out. Okay, now let's let this value go beyond 1 and see what happens. So you see when my beta value goes beyond 1, the maximum will now happen outside of the first region. As you can see, it's about 1.2. That means time is about 1.2 times T1. All right, so you can keep on playing with this and see for yourself that it is when beta is smaller than 1 that the peak happens within region 1. Otherwise, okay, perhaps let me move this slider. Okay, let's see that again. When beta is some value smaller than 1, you see that the peak happens within region 1. But once beta goes beyond 1, the maximum or the peak response happens outside of the load application region. That means T from 0 to T1. That's where the load is applied. Okay. So that's a general observation that we make. And that's the end of the video. Thank you for watching.